When we took a look at the idea of entropy, we learned that entropy is a measure of average surprise given the outcomes of a probability distribution. Sometimes what we want to do is we want to compare two probability distributions for the same random variable. This is called cross entropy when we do such a thing, or this is one measure of doing such a thing. And so imagine we have two probability distributions on random variable x. So we have a belief about the random variable, and we believe that the distribution is distribution Q. Okay, so we have this random variable, and we believe that the probabilities are distributed one way. But actually we learn that the random variables are actually distributed according to a different distribution. On average, how surprised will we be by what actually happens in relation to what we believe is true? So how surprised are we going to be given some real outcome based on how we believed it should happen in the first place? Well, this is called cross entropy, and it's really defined in a very, very similar way to the entropy itself. So let's use some abbreviated notation rather than to call this entropy like we did before. Let's call that function h. Okay, so h of p was the negative sum of the probabilities times the log of the probabilities, and we derived this whole expression from root principles, where p of x is the probability that random variable x takes on value little x. So basically we just have to sum across all of the events of that distribution. Now cross entropy is that we take the log of our believed probability, but this is the believed probability, and this is the actual probability. Now, one thing that I want you to notice is that the cross entropy between a distribution and itself. Okay, so imagine that we believe distribution Q, but we believe distribution P, but actual is also P. Okay, so in that case, the thing that changes in the cross entropy is that the distribution that we believe in and the actual distribution are the same. And the reason I mention this is because, well, in that case, the log probabilities come from the second distribution. And if the distribution is the same, then you get the sum across all events, p of x log of p of x. And so the cross entropy between p and itself is just entropy. Okay, and so what we might naturally expect, and this is a fact, by the way, that h of p comma q is greater than or equal to h of p. For one, if the distribution is the one that we believe and the one that is true is the same distribution, then they're going to be equal. But in general, we're going to experience more surprise because now we have a belief of one distribution, and then an actual distribution is something that we actually learn about, and we find that we're probably going to be more surprised than by knowing the probabilities as they are. So I'll illustrate this. So p of x is the probability that x equals x according to distribution p, and q of x is the probability that x equals x according to distribution q. So for example, let's suppose we have a coin we believe is fair. So easy way to remember that it's Q is we're questioning our belief, right? So Q question, but is actually biased. So the actual probabilities of getting heads is 0.7 and tails is 0.3. But we believe that it's fair, right? We believe, and this is the actual. So if we compute this, and I've already written that out here, so it's p of x log, and we're, remember, using base 2 because there are two outcomes. This is just kind of standard by convention. And so it's the negative sum of p of x times log of q of x, and then repeat that for the second event as well. We get a surprise of 1. So on average, we have our average surprise is 1 based on what we believe compared to what is the actual outcome. However, what would happen if this discrepancy were even greater? So let's say that the bias is actually much bigger, 0.99 of heads and 0.01 tails. So maybe it's, I don't know, somehow most of the time lands on heads. And q of x, still our belief is that it's a fair coin, but the actual is an extreme bias. Okay. Well, if you do the computation on this, you get a surprise of 1 again, right? So look at these two. And these are the same. That can't be, right? Because if we believe something is fair and it's actually completely unfair compared to the 0.7, 0.3 case where, yeah, it was biased, but it wasn't as bad as what we would get here. So here we would probably get, in 10 tosses, we'd probably get 10 heads, and we'd be very surprised compared to if we were to get, say 6 heads and 4 tails, we wouldn't be that surprised. So what gives here? Well, as mentioned, we already have the built-in entropy in the cross entropy function. So we should definitely be more surprised in case 2, intuitively speaking. Now, we've already noted this, that distribution P has its own degree of surprise, right? There's just surprise by the outcomes themselves. So we are actually factoring that in when we compute the cross entropy. So somehow we should strip that away, right? We should strip away any surprise created by the actual distribution itself. So we do this by taking the difference between the cross entropy and the entropy inherent in the actual believed distribution, right? Because this is just surprising. To get a tails would be very surprising in and of itself. So that 1 is inflated by the surprise that comes in from the outcome of tails. So we've already noted h of p comma q is greater than or equal to h of p, which is pretty intuitive since h of p q already contains entropy in it. So to take this difference, that is called the Kullback-Leibler divergence, or for short we call it KL divergence. And we write it this way. We say that the divergence d sub KL between p and q, it's going to be the cross entropy minus the entropy associated with the actual distribution itself. So this is the surprise in the difference between the two distributions. Okay, so how do we get this formula here? It's the sum of p of x log p of x over q of x. Well, I just want to show you that if we take h of p comma q, okay, so using this definition here, if I now take h of p comma q, which is the sum across all x of the believed, I'm mixing things up here, p of x times log of q of x, as defined back up here, and that is going to be, we're going to subtract from that the sum across all x of p of x times log of p of x. Okay, so I just want to show you where this very formula actually comes from, because it looks nice and condensed. There's no subtraction signs, but it all starts with this. Now we can pull out the summation because it's still going to add up across all of the x's. And we can actually also factor out a p of x from both of these. So we get log of q of x minus log of p of x. And the difference between two logs is the ratio of the arguments. So we would get the sum across all x of p of x times the log of, and I'm sorry, I should have negative signs here. I should have a negative sign on both the entropy and cross entropy. So this is the negative sum. And we're subtracting away, so this becomes a positive. This is a negative. So it's actually p of x minus log p of x minus log q of x, which is log of p of x over q of x. And there is our DKL between p and q. So if we take this into account, you'll notice much more satisfying results. The uncertainty in case 1 is, or the surprise, is a low average surprise, whereas this is many times higher, right? This is almost about 8-9 times higher. So this is we'd be highly surprised in this situation if we assumed that the coin is fair, but we get 10 heads out of 10 tosses. We have high average surprise, and it's almost, we'll just say, about 8 times higher, which makes sense, right? Much more extreme. So DKL can be thought of as the measure of surprise caused by the difference in distributions while eliminating the uncertainty of the actual distribution itself.